There are different types of blood flow, the laminar, that is streamline flow, and turbulent blood flow in the vessels. Laminar blood flow, the blood flow in a large number of layers at a steady rate, with each layer remaining at the same distance from the vessel wall. For example, characteristic of most part of the vascular system is laminar blood flow. Turbulent blood flow, here blood flow in all direction in the vessel and continuously mixing within the vessel. Thus, there is a greater energy loss compared to the laminar flow. For example, in the ventricles and in aorta, there will be uh, turbulent blood flow. Okay. So here you can see actually the blood is in streamline. There are different layers with the different velocities. The central layer has a maximum velocity compared to the lateral, and this is the turbulent flow where the blood flow occurs in many direction. The Reynolds number, where the turbulence is given by Reynolds number. Reynolds number is equal to Vp into d divided by mu, where v is equal to velocity of flow in centimeter per second, p is the density of the blood, d is the diameter of the blood vessel, and mu is viscosity of the blood in poise. When the Reynolds number is less than 1000, the flow is always laminar. As the value increases, the probability of turbulence also increases. The turbulence develops when the Reynolds number exceeds 2000. In anemia, viscosity is decreased and systolic murmur is heard while auscultating the heart. Flow of blood through the vascular system is governed by a group of physical laws. Bernoulli's principle. It states that a tube or blood vessel, the sum of the kinetic energy or flow and the pressure energy is constant. Therefore, when fluid flows through the narrow portion of the tube, kinetic energy of flow increases as the velocity increases and the pressure energy is reduced. That is, the standing pressure decreases. Thus, greater the velocity of flow in a vessel, lesser will be the lateral pressure distending its wall. Laplace law. Laplace law is a relationship between the distending pressure and the tension on the wall in a hollow viscous object. It states that distending pressure, that is pressure in an distensible hollow object, is equal to the tension in the wall divided by two principal radii of curvature of object, that is R1 and R2. So P is T divided by R1 plus T divided by R2. In a sphere, in a lung alveoli, the radius 1 is equal to radius 2. Therefore, pressure becomes 2T divided by R. In a cylinder such as blood vessel, as one radius is infinite, therefore P becomes T by R. The physiological significance of law of Laplace here is, smaller the radius of the blood vessel, lesser the tension in the wall necessary to balance the distended pressure. So this is why thin-walled and delicate capillaries are less prone to rupture.